I'm Dave Ockley. I'm going to tell you about computing the area of a parallelogram and actually also tell you about the determinant. So if we have a parallelogram and we describe the edges by a vector x, and you sweep around counterclockwise to get to a vector z, then the area between the parallelogram spanned by these vectors satisfies a property that if we stretch one of the vectors, say the x vector, by a factor of 3, that the area gets 3 times bigger. In general, I can factor out a constant from the first term or a constant from the second term. That's the first property that area satisfies. The second property, if you think area is like length times width, you might expect that this z could distribute across the x plus y to x times z and y times z, and vice versa the other way, which indeed it can. Here, if I've got the vector x plus the vector y to get the base, I can recolor this gray parallelogram into pieces to make it look like this. And if we move the red triangle up to the top, we see that the result is the same as two separate parallelograms, the area of xz plus the area of yz. In summary, we saw that the area distributes vectors like this, according to the bottom. Those are the second two formulas. The third formula is a little bit more, well, I'll say gruesome. Let's imagine what happens if you've got a parallelogram and the two edges are the same. If the two edges are the same, it means it got flattened. Godzilla came around and stepped on it. And so when Godzilla steps on it, you see that it has 0 area. And this rampage is going to have consequences. One of those consequences we can see, if I take the area of x plus y and x plus y, that's 0, it was flattened. Then we can distribute, pulling the second term times both of these on the left, x plus y, x plus y. And then we can distribute in the other direction, and we see that the first step term had been flattened, and the second last term had also been stepped on. So if we solve for the area from y to x, we can just bring this to the other side, and we see ayx is negative axy, which means that when you switch two things, you pick up a negative sign. That negative sign may seem a little bit weird to you, but this is actually an oriented area where you would count area as positive if you sweep in the counterclockwise direction to get from the first vector to the second. So that's all we need in order to compute the area of a parallelogram, because the area of the parallelogram was edges given by this vector AB and CD. Well, we can write AB is A times 1, 0 plus B times 0, 1. Then we can distribute this through and pull out the constants, as in that second row. We can write CD as C times 0, 1, or 1, 0 plus D times 0, 1, and then distribute there, getting this big long line. But in this big long line, we notice that this thing has seen our monster and has been flattened. And our friendly monster is flattened to this term. And the consequence of the rampage is that when we turn these two vectors, switch their order, we pick up a negative sign, which gets us this bit here. Of course, the area of 1, 0, 0, 1, that would just be a little square here, which is just as area 1. So we end up with just AD minus BC. This is such a common problem, it makes sense to define this to be something. This is the definition of the determinant of the matrix ABCD.